And at least first two tutorials we're going to do online because of the current situation. It's Omicron. And yeah, let's get started. So last time you discussed the signal space and how you can calculate the basis for such signal space if you are given with a set of arbitrary signals. And you discussed the Gram-Schmidt orthogonalization procedure. Today we're going to solve extra tasks on this topic. And if you have any questions, please let me know. You are welcome to write in the chat, and you can also try to open your microphone. But unfortunately, our experience with open microphone is not very good. Maybe it's better if you type your question in the chat. Okay, let me share my screen. And we start. So we actually today and tomorrow we have another tutorial. We're going to solve all questions from previous exams. And I would like to start today. I would like to start with the task from 2016 on signal space. So we have the following task. Let me read it first. We have a set of signals. We have 4 possible transmit signals, and all of them restricted to the interval from 0 to capital T. Capital T is simple duration. And then we have multiple questions. We need to find orthonormal basis. We need to find mean energy per symbol. We need to plot the decision boundaries. And then we need to find minimum distance, minimum Euclidean distance between neighbor symbols. So let's get started step by step. So this is task number 2 from 2016. I think you can find this exam online in Moodle. And there you can find the following set of signals that we can transmit. So we have pulse from 0 to t over 2. And then we have 0. Our signal 1. Second signal is negative pulse from 0 to t over 2. It's our second signal with amplitude minus u0. For the third signal, we have pulse that starts at t over 2 and goes to up to capital T. And all of them, they have amplitude u0. And the last pulse also goes from capital T over 2 to capital T and has negative amplitude. This is a set of signals that we have. Minus u0. And we need to use the Gram-Schmidt procedure in order to obtain an orthonormal basis. We need to draw the basis functions and specify the signal vectors as I. The parameter n is the dimension of the signal subspace. Yeah. We need to find basis to represent all these signals. And basis itself is not unique. You can have multiple different options for basis. So For this reason, depending on starting from which signal you, depending on which with which signal you start, you may have different set of orthonormal vectors. And we start with Gram-Schmidt orthogonalization procedure. So we have multiple steps, and I will show how it works in all details for this example. So let's assume we have set of signals as we have on this in this task. For Gram-Schmidt orthogonalization procedure, we perform multiple steps. In the end, we get orthonormal basis, and always we start assuming that our first basis function is the same as our first signal. So simply speaking, you say that your first signal is nothing else as scaled version of first basis function. We have scalar S11 that changes amplitude of our basis function. But always we say that, of course, you can choose any signal you like as first for your first basis function. But the obvious choice will be to say that first signal is the first basis function. So as a result, as you can sequence, we can find basis function psi 1 of t if we take our first signal, or it would be better say the corresponding signal, and normalize by scalar S11. And this scalar S11 we can find, or we can represent it via energy of signal S1. So simply speaking, if we take energy and calculate square root of it, then we get this scalar S11. And from there, or like based on this, we just need to calculate energy to find the scalar S11. So energy is integral of squared value of our signal over time. And for such signal that we have above, you see that it has constant amplitude up to time t over 2. And energy will be equal to area or under the envelope. We have u0 squared times t over 2, duration of our pulse. So this is the energy. So then we find scalar S11 as square root from energy, and will be equal to u0 times t over 2 under square root. And normalizing our first signal by this constant, we can show what will be the first basis function. It has the same shape as our first signal. So it will be pulse that goes, maybe I show this slightly different amplitude. It is pulse that goes from 0 to capital T over 2, but it will have different amplitude. And why it has different amplitude, or why it has to have different amplitude, why we don't take our first signal as it is? Because, by the way, I should write first, it will be 2 over t under square root. This is the value of our amplitude of our first base function. The reason why we have to normalize is because energy of basis function, which is again integral from 0 to capital T of our basis function squared, must be equal to 1, because we're talking about orthonormal basis. So orthogonal basis means that we have all vectors orthogonal to each other. Orthonormal basis means that the norm of each vector in this basis, or energy of each component, each vector in this base equals to 1. This is our requirement. This is constraint, and it allows us to simplify some steps later on. Okay, so we have found first the basis function, and we see that it's nothing else as a pulse that goes from 0 to capital T over 2 and has amplitude 2 over capital T under the square root. Okay, this is the end of first step, and we go to the second step. Second step, at the second step, we make the following assumption. We say that our second signal represented by weighted sum between two basis functions. So we take some part of first basis function, and we have some part from second basis function. And based on this assumption, we can find second basis function. So this is our assumption. And we can find coefficients S21 and S22 using the following expression. Sij equals integral from minus infinity to infinity Si of t. So we take ith signal and we multiply it with j's basis function. This is how we find the scalar Sij. Now we just need to substitute what we know about, or we need to substitute indices I and j, and we find the corresponding scalars. Okay, let's do it. What actually we're going to do, or maybe not to do what, but what we know about the expression above. We know basis function psi1, and we know how our second signal looks like. We don't know scalar S21, but we can find such scalar by the expression below, and we don't know S22 and psi2. And actually, this is our goal, to find psi2. So our goal is to find second basis function, and we're going to calculate this basis function, second basis function. Actually, we're going to find product between S22 times psi2 of t as difference between second signal minus S21 times first basis function. And in order to find this normalized, or no, in order to find this weighted version of second basis function, we need to calculate difference on the right side. But for this difference, we don't know scalar S21. And now we're going to find this scalar. Using expression above, we can say that scalar S21 we can find as integral from 0 to t. I replaced this infinite limits by duration of our signal. And then we say that we calculate cross correlation between our second signal and first basis function over time. And it's not difficult to see that if you take, let me copy the second signal. If you take second signal, and first basis function that we have found previously, I will show them like this. You see that actually second signal is just normalized version of our first basis function. So, and we can calculate integral. Again, we narrow our limits. We make them smaller because starting from t/2 to capital T, we have a 0. Our signal equals to 0. We have minus u0 amplitude of our pulse times amplitude of our basis function over time. And as a result, we get that this cross correlation equals to u0 times t/2 under square root. And we can find, now, next step, we need to find explicitly what's the value of S2 times psi2t as difference between second signal and a weighted version of first basis function. So I'm going to plot second signal. Minus u0 as amplitude. It goes from 0 to capital T. Then I will plot how my weighted version of first basis function looks like. It will be minus u0 times square root of t/2 under square root times 2/t under square root. And if we multiplied all these scalars, we get that our resulting amplitude will be minus u0. Our product S21 times first basis function. And you see that second signal and this product equal. And as a result, the difference between these two equals to 0. There is nothing left for difference. The difference equals to S22 times psi2 of t. There is nothing left. And we can say, based on this, that actually we don't need second basis function in order to represent the second signal. As a conclusion, we say that our second signal can be represented by a first basis function. So it's just the first basis function multiplied by S21, where S21 equals, and then we just write as the scalars that we have found previously, minus u0 times t/2. This is what we have for our scalar S21. Okay, so we made, it's the beginning of this step, we made the assumption that we need to have two basis functions in order to represent second signal. But as a result, we got that we don't need second basis function, we just need one basis function. It's fine, it's not like something that ruin our solution. We just made assumption and we get slightly different result. Okay, but now we go to third step and we come to third signal. And we actually, up to now, we have only one basis function. And for every next step, we try to increase the number of basis functions for one additional basis function. And if we didn't need any extra basis functions for previous step, then it might happen that we need another basis function to represent third signal. And then we make another assumption that third signal it could happen that we need to have two basis functions to represent third signal. So maybe at this step, we get second basis function. And again, this is our assumption that we make in the beginning. So as before, we need to find the corresponding cross-correlation scalar S31 between the third signal and first basis function. So we have S3 of t times psi1 of t times dt. And yeah, here now we get actually interesting result that we take our, I will again copy, I will make another copy for third signal. And I will place below second. Sorry, first basis function. We have only one basis function so far. And if you look to third signal and to the first basis function, you see that actually they not overlap. So our third signal goes from capital T over 2 to capital T, but our basis function goes from 0 to capital T over 2. We don't have any overlap, and we can say that this product will be equal to 0. It will be equal to 0, and it means that third signal and first basis function orthogonal. S3 orthogonal to first basis function. And it means, if they're orthogonal, it means that our third signal is nothing else as weighted version of a second basis function that we don't know yet. But we know that if we just normalize our third signal, then we can get our second basis function. So we take our third signal and we normalize by energy of our signal, this scalar S32. For this case, nothing else as energy of our third signal under square root. So, and formally speaking, we have to write that it's cross-correlation coefficient, but as far as we have only one component, it will be energy. But let's keep it in correct way. So we write that it will be energy or value of cross-correlation scalar S32 that we calculate. But yeah, anyway, here we have to calculate energy. So we calculate an integral from 0 to capital T, S3 of t squared times dt. And then we see that our signal, third signal, has amplitude u0. So we have u0 squared times capital T over 2. And from where we can find that this scalar S32 equals to u0 times t over 2 under square root. And then once again, we write that our second basis function is third signal normalized by S32. And from where we get our second basis function, and I can show it by plotting corresponding figure. So it will have amplitude 2 over t under square root, second basis function, and it goes from capital T over 2 to capital T. And by the way, we can actually show, let's calculate energy for such a basis function. If we calculate energy of second basis function, integral from 0 to capital T of second basis function squared times dt, we get that we have 2 over capital T under square root squared times duration T over 2. As a result, it will give us 1, and you see that energy equals to 1. So it will have unit energy. So, fine. And for the fourth step, for the last step that we have, we need to consider last signal that we have. And we need to perform again the same steps as before. So here, let me write what we do at the beginning, but I don't write solution for it. I will take shortcut. For the last signal, we have to make assumption that our last signal includes 3 basis functions. So we say that it will be a weighted first basis function plus weighted second basis function and plus third basis function that we don't know yet. And this is our assumption. So every next step, we increase number of basis functions that we need to discover, or that we have to represent all these signals. And then you just repeat all the same steps that we did before. But obviously, I mean, looking to this picture, to this signal, of course, you can see that it's nothing else as just the weighted version of second basis function. And you don't need to perform. Actually, also, sometimes I get questions if you need to repeat all these steps that I show at seminars. Of course not. I show all these intermediate steps just to explain how it works and what's the idea behind it. But during exam, you just need to solve everything as fast as possible. And very often you can skip many of intermediate steps. So here we see that actually the last signal is the negative version of third signal, of previous signal. And as a result, we can conclude that to represent last signal, we just need second basis function that we normalize by scalar S42. And we can also say that this scalar S42, because the difference only in sign, is nothing else as negative version of scalar S32. And in the end, it will be equal to U0 times T over 2. So that's all. I mean, of course, you can repeat all the same steps that we did before, and you get exactly the same results. But here I show you shortcut. Okay, that's all for first part. For the second part, B, determine the mean energy per symbol and the mean energy per bit. So mean energy per symbol ES and mean energy per bit EB. So we need to find these quantities. I introduce intermediate variable E0. It's energy of our symbol, or actually it's not energy of one symbol, but it will be product between U0 squared times T over 2. This quantity corresponds to energy of any symbol that we have for this task. But in general, it might happen that for different symbols, you will have different energies. It also may happen. But in order to simplify our notation, I introduce such quantity. And I also notice that energy of first signal, the same as energy of second signal, the same as for third, and for fourth signal. And all of them equal to E naught. So all of them the same, only for this task, not in general. And I can say that my average mean energy per symbol is nothing else as summation of all possible energies for different signals divided by number of symbols. So, and of course, if you just replace this summation by exact values, you will get that this is nothing else as E0 for such example, for this example. Okay, and if you need to calculate mean energy per bit, you can simply use mean energy per symbol and divide by number of bits that you transmit with each symbol. And look at our constellation or to our set of signals. We have 4 signals and we have 4 possible positions. And in order to describe all these 4 possible positions, you need to have 2 bits. Yeah, you can encode each symbol with 2 bits. And as a result, for each symbol, you carry 2 bits. So, and mean energy per bit is mean energy per symbol and not divided by number of bits that we have for each symbol. It's 2. And if I substitute exact expression, it will be U0 times capital T, U0 squared, of course, times capital T, divided by 4. This is mean energy per bit that we have for this task. Okay. Yeah, that's all for part B. Then we go to part C. Draw the signal space diagram and indicate the decision areas. For instance, fill out with different colors for optimal detection in AWGN. All signals have the same probability. Okay, I think I forget in part A, we had to specify signal vectors as I. We forget one small part for part A, but we can do it now. We can do it now. I will just write that we're talking about part C. And remember that we just write how we can represent each signal. First signal was nothing else as S11 times psi1 of t. But we can write that we have first part plus 0 times second basis function. I mean, nothing changes because we add just 0. But it will help us to somehow unify our notation. And this sum of 2 products, we can rewrite in matrix form or vector form. We can write it as inner product between 2 vectors, between vector which contains scalar S11 and 0 times vector which contains 2 basis functions. We can represent it in this way. And the part that we have in front of vector with basis functions, we call as vector of our signal. So our signal represented by a vector which comprises scalars in front of each basis function that we have. And for this example, we have only 2 basis functions, but in general, you have infinitely many different basis functions. So you don't have any limits on the number of basis functions. Okay, then for second signal, and by the way, we can also say that this scalar S11 was equal to E naught under square root. And if you substitute instead of E naught value in terms of amplitude, you can find what's the amplitude. But I will keep it as it in terms of E naught. Okay, if we go to second signal, we do all the same. So our second signal is S21 times psi1 of t. Again, plus 0 times second basis function. So whenever we encounter that we don't have second basis function, we just add it by multiplying by plus basis function multiplied by 0. And we can write it as S22, 0, and again the same vector with two basis functions. This inner product. By the way, I made a small mistake before. It is not simply vector S1, it is vector S1 transpose. It's quite important because if you say word vector, it means that you assume column vector, because otherwise sometimes it leads to ambiguity. Do we have column vector? Do we have row vector? And always, at least in our program, in our MSSP program, when we say word vector, we assume column vector. And if you want to get a row vector, then you have to transpose it. Okay, so it will be S21 in the matrix C. Okay, yes, I made small typo. Thank you. It should be S21. Of course, it will be S21 and S22 second element equals to 0. And it will be our vector that describes second signal, S2 transpose. Okay, then we go to third signal, S3 of t. And for third signal, we had actually quite opposite situations, that we didn't have first basis function. So we have 0 times first basis function plus, and then we have S32 times second basis function. But the algorithm is the same. We just represent it as inner product times vector with basis functions. And the last function, before we go to the last function, actually I should write values for S21 and S32. If we go back, S21 was here. This is S21, and we can write it as minus square root of E0. And for S32, that was here, we can write it as square root of E0. So, minus square root of E0 and plus square root of E0. And for the last function, for the last signal that we have, S4 of t, it equals, again, we have 0, nothing from first basis function, plus S41, no, it's not 1, it's 2. But did I write 1 before? No, it was written 2. No, it was 5. Times psi2 of t. We have 0 and S42 times psi1 of t, psi2 of t. And this S42 equals to minus square root of E0. So this our previously it was vector for third signal, and now we have vector for our last signal, S4. And now using this vector representation of all signals, we can plot so-called signal space diagram. It is plot where for axis you have different basis functions. On the picture we can show only 3 basis functions at most, but in general again you may have as many basis functions as you need or as you want. And because the orthogonal, I show them as perpendicular lines, and for one axis I have the first basis function, for another axis I have second basis function, and then I just need to denote some unit interval or scaling. I say that let's say 5 cells will be quantity square root of E0, and for each direction I specify where I have square root of E0. And using these points, I can actually, they should be not arrows, but they should be simply points at the beginning, because I just specify scaling. Just points, they don't correspond to any signals. And now I need to match, make matching between my signals and points on this plane. So let's start with the first signal. We have signal S1 of t, and it has 2 components, square root of E0 and 0. So we just, for first basis function, we take square root of E0. For second basis function, we have 0. As a result, I can show a vector that starts at origin and goes to the point square root of E0 and 0, this green arrow. And this green arrow corresponds to our first signal. If we go to second signal, S2, we have minus square root of E0 and 0. So again, we start at origin and we go to the point minus square root of E0 and 0. This is our second point, S2. So it corresponds to the signal S2. Third point, or third signal, has coordinates 0 and square root of E0. So we start origin and go to point 0 and square root of E0. This point corresponds to third signal. And last, again, we start at 0 and go to 0 and minus square root of E0. This point corresponds to S4. Now you have the signal space representation for the set of signals that we introduced in the very beginning. Okay, we have signal space diagram. Now we need to specify decision boundaries. And I would recommend you, when the question becomes, when they ask you about decision boundaries, plot them explicitly, because sometimes they're not, they're very tricky. And actually next task, if we have time, you will see that it's sometimes it's tricky to find such boundaries. So what you're doing, you need to consider all pairs of symbols. No, sorry, not all, but all nearest pairs of symbols. So what's the nearest what the pairs, or like it's pairs that we have that have minimum possible distance. It will be pair S3 and S1. It will be S1 and S4, S4 and S2, and S2 and S3. These pairs, they have minimum distance. We don't consider pair S3 and S4 because such pair is not nearest. We can find another pair that we have smaller distance between 2 points. And then after we determine pairs, for example, S3 and S1, we determine middle point and we plot a line orthogonal to a line that connects these 2 points. So this line corresponds to boundary in decision between point S3 and S1. But also the same line will be decision boundary for S2 and S4. Okay, then if we consider points S3 and S2, again we determine middle, and then we plot orthogonal line that goes through this middle point. So, and this is our another boundary, decision boundary for points S3 and S2, as well as for points S4 and S1. And I just tried to find if I have something sophisticated. Yeah. Okay, let's try to use yellow. Okay, it's not so bad. Okay, with this yellow, I show first decision boundary that we made. Oops. But keep in mind that it starts at origin, but because of this special features of the tools that I use for drawing, I'm not able to reach origin with this marker. Okay, this is our second decision region. And I can continue further. This is the third decision region. And the last decision region I will leave as it is with this, let's say, white or transparent color. We have these 4 decision regions. Okay, fine. And then for question D, it was everything about D. Sorry, before it was everything for C. Now for part D, as I asked to find Euclidean distance between different signal vectors. I will repeat the same diagram. Sorry, we have points aligned with our axis. So we have S1, S3, S2, and S4. Now we need to find Euclidean distance. So we need to find what the distance between different points. And we have distance between, for example, S1 and S4. The same distance will be between S3 and S1, as well as between S2 and S3, and S2 and S4. This is one set of distances that we have for this example. But we also have another set of distances. We have distance between S3 and S4 and we have distance between S2 and S1. And we can find these distances if we take into account that energy of each signal is square root of, let's say it's not, we can write it in terms of mean energy, square root of ES. Then we can specify that distance between S1 and S2 equals to distance between S3 and S4, and it equals, and we just need to take twice this energy that we have. It will be 2 times square, sorry, not the energy twice, but distance twice that we can find via square root of energy. 2 times square root of energy. For distance S3 and S1, or all these connecting nearest points, S1 and S3 equals, and then 3 other options. We can find it if we use Pythagorean theorem and we calculate this third side of the triangle, and to be equal to 2 times ES under square root. And you see that opposite points, they have larger distance than nearest points. Yeah, and these nearest points will determine what the quality of transmission you will have. Okay, and the last part E, we need to specify this minimum distance as function of mean energy per bit. So we can simply write that D mean, that is this is the minimum distance between nearest neighbors, and it was 2 times ES under square root. But we remember that ES equals to other way around. EB equals to ES divided by number of bits, in our case 2. Then we get that we have 2 times EB it should be multiply times EB, and as a result we have 2 times EB under square root. So this is what we get, and this is the result for last part. Okay, are there any questions about this task? This is task from 2016. Okay, if there are no other questions, we don't go further. There are also other questions, but we didn't discuss yet anything about symbol error rate. And we come back to this, or we may have come back, but not necessary because we have other tasks later in our course. Okay, but now I propose to go to another exam. And now we're going to talk about exam from 2013. Task number 5. This task from February of 2013. Oh yeah, it was interesting date. Yeah, a unique date for this special exam. Okay, we have the following problem, that we assume that in time interval from 0 to capital T, so we have that our observation time from 0 to capital T. We have 5 signals. starting from S1 of t up to S5 of t. And also we say that these signals can be represented by means of the signal vectors from S1 to S5 and the basis functions. Oh, and it's specified that you have only two basis functions, psi1 and psi2. According to the figure, only one of the two orthonormal basis functions is known. So it is given that you have two basis functions and one of them is given. There is a question. Okay, if it's not available, it's not a problem because you always can solve other tasks from other exams. So this is, you can treat it as a bonus. Okay, you know that first basis function has the following shape, but you don't know what's the amplitude. So it goes from minus k to k. And k is not specified. It's unknown. And you don't know anything about second basis function. Second basis function is not defined. We know that it exists, that we need to have two basis functions, but we don't know what's the shape of the second basis function. And now we need to solve this task for the following questions. First of all, we need to determine what's the constant k, what's the value of constant k. So, and again, we use the property of basis functions that they're orthonormal, that they have unit energy. Integral from minus infinity to infinity of our first basis function or any basis function squared over time must be equal to 1. And we know how this base function looks like. So let's write the energy of this basis function and try to find the corresponding scalar k. So we can write that energy of basis function, it's integral from okay, strictly speaking, we have two parts in our basis function that have different signs. But I will simplify because when you calculate square value, you just drop sign, yeah? And I can just write that we have integral from 0 to t of k squared times dt. Yeah, I will, of course, you could just split integral and write integral for each part separately, but the result will be the same because the sign will be we neglect sign because we calculate square value. And as a result, you see that this energy equals to k squared times duration capital T. And it must be equal to 1 by definition for basis function. And from where we can find that k equals to 1 over capital T under square root. This is our constant for first basis function, or amplitude for our first basis function. And I can show again the basis function. It goes from 0 to capital T, and it has amplitude 1 over capital T under square root. So now we have full information about first basis function, but we don't know, still we don't know what's the second basis function. So second question that we have, we need to draw the following signal. S1 of t equals, and then we have signal 2 times u0 times rectangular t minus capital T over 4 divided by capital T over 2. So this is our signal, our first signal. And let's plot it. So it goes, it has a center at the T over 4. Center is here, and it has width T over 2. So as a result, we can see that it goes from 0 to capital T over 2. We have pulse in this range with amplitude 2 times u0. This is our first signal. Okay, great. And what else? And actually, that's all. That's all for part B. We just need to draw the signal. We come to part C, and we need to find a basis function psi2 in order to represent our first signal by means of vector S1 in the signal space. So we have signal S1. We need to represent the signal with two basis functions. We know first one, we don't know second one. So this is just a canonical question for Gram-Schmidt orthogonalization procedure. And we just write one of steps our procedure. We have signal S1 that we can represent via two basis functions, S21 scalar for first basis function plus S, sorry, it's not 21, it's 1, 1 times first basis function plus 1, 2, 1, 2 times second basis function. So assume that we have two basis functions. We know what's the first basis function, but we don't know the rest. We don't know what's the product. We don't know what's the S11. And also we know what is signal 1 itself. So let's following our previous procedure, we need to find first scalar S11 as cross correlation between first signal and first basis function, and let me copy our first basis function and place it below. I will align them, and you see that our first signal overlap our first basis function only in the range from 0 to capital T over 2. And at T over 2 up to T, overlap will be equal to 0. As a result, I can slightly modify this integral and write that we need to calculate integral from 0 to capital T over 2 of 2 times u0 times 1 over square root of t times dt. And as a result, we get that it gives us u0 times square root of t. This is what we get if we calculate this integral. So now we can find what will be the difference S12 times second basis function, and it will be equal S1 minus S11 times first basis function. Now we need to plot and try to evaluate this difference. So we have our signal S1 that goes from 0 to capital T over 2 with amplitude 2 times U0 minus and I need to calculate product between S11 and first basis function. So our basis function has amplitude 1 over capital T under square root times U0 times square root of T gives us amplitude U0. And this is how our product will look like. So it will be 2 times smaller than our signal S1. And if we subtract second part from the first, you see at what you get. Yeah, we should do it for each region separately in order to avoid any mistakes. So we have region from 0 to capital T over 2 and from T over 2 to capital T. This is product S1, 2 times second basis function. So if we consider first region, we have, of course, amplitude is constant in this region. We have 2U0 minus U0. The result will be U0. This is amplitude for first range. Okay, let's go to second range. We have 0 minus U0. So minus with minus gives us plus. And for second region, we have also amplitude U0. As a result, you see how this difference will look like. It will be rectangular pulse that goes from 0 to capital T. Okay, we have found the product. And now, just following the same idea that we did in the previous task, that if we have a difference, we simply need to normalize this difference in order to find our second basis function. So we said that our second basis function, it will be written I mean, it looks silly, but the idea that we unfortunately not able to find inside this product, we can find the whole product, but we're not able to find separate parts. So we have this product, and then we need to normalize it by S12 that we have to find. We can rewrite this as S12 times second basis function normalized by energy of S12. Okay, and we need to find energy S12, and we can find it as integral from 0 to capital T. U0 squared times dt, and it gives us U0 squared times t for energy of the remaining part. So, and we can find okay, we can just write it from where square root of S12 equals to U0 times square root of t, and just we don't find anything else, and then we plot how our second basis function will look like. So our second basis function will be rectangular pulse that goes from 0 to capital T, center at T over 2, and which have which has amplitude 1 over t underscore. This is our second basis function. Okay, great.
Professor?
Yes, other questions?
Can you?
Yes, I can hear you. Yeah.
Can you please
ask your question.
explain why the energy of ES12 is equal of?
No. Who is speaking it?
Vivek. I am Vivek.
Something. Yeah. Yeah. If you come closer and try to speak louder, then I can hear you. Yeah.
Okay.
Just,
now
do it louder.
audible? Is my voice audible now?
Yeah. Now it's better.
Okay. Can you please explain why energy of ES12 is integral of U0 square dt?
Yes, you're right. It's not wrong. But I mean, it's not energy of S12, strictly speaking. Okay, yeah. I should write that it is energy of S12 times psi 2 of t. So it's energy of the remaining part. S12 times psi 2 of t. So it's not just a scalar, but it's a signal. Yeah, because it's a scalar is just scalar. We don't calculate energy of the scalar, but this is energy of the remaining signal that we have. Yeah, is it better now? Or still question why we calculate like this?
Yeah, now it is better.
Yeah.
Thanks.
I just tried to didn't overload notation, but you're absolutely right that we don't take simply S12, but we take this energy of the remaining signal in time domain that we have. Okay, fine, we can go further. And what next? Okay, next we need to represent, yeah, actually it was the original question. We need to represent this signal as S1 in vector form. And S1 of t equals to S11 times psi 1 of t plus S12 times psi 2 of t. And we can denote the quantity. We can denote the quantity U0 squared times t as E0, as we did previously in the previous task, S11. In this case, S11 will be nothing else as square root of E0 if we do this. E0 equals to U0 squared times t. And we can rewrite our this weighted sum as square root of E0 under square root for first part, first component. For second component, we have also square root of E0 under square root times psi 1 of t, and second component psi 2 of t. Okay, and the square root of E0 under square root is often called as U0 times square root of t, U0 times square root of t. Okay, fine. And actually it was question D. It was question D, and we can say that this part inside this parenthesis is nothing else as S1 transpose. And we can write that S1 in vector form, we don't have t anymore, can be written as square root of E0, E0. So this is how we denote column vector in our master program. So we go to next question, question E. We need to draw the time domain signals, and we have 4 different signals. So we have signal S2, which is given as 0, 0 transpose. Then we have signal S3, which can be written as minus square root of E0 and E0. Transpose the next signal 4 minus square root of E0 and minus E0 transpose. And the last signal that we have is S5, which is given by square root of E0 and minus square root of E0 transpose. Okay, we have 4 signals. Actually, we have 5 signals. And we need to draw signal space of all these signals. Yeah, E0 defined our previously. It is nothing else as U0 squared times capital T. And we can draw the signal space diagram. Okay, we have one basis function, another basis function, and we need to show all, and we have all plots here. So we can say 8 cells correspond to square root of E0 on each axis. And now we can try to show all these signals on this signal space. We start with signal 1, of course, S1. And it has coordinates square root of E0, square root of E0. So this is the point where we place our first signal, S1, and it's represented by a vector that goes from origin to this point. This is our first signal, S1. Then we go to second signal, S2, and signal S2 located at origin. I will show it with this bold point, which corresponds to signal S2. This is our signal S2 located at origin. Then we go to next. Next is signal S3, given by minus square root of E0 and square root of E0. So along first axis, we have to take minus square root of E0. And along second axis, we have to take plus square root of E0. So this is the point which corresponds to our third signal. S3. Then S4, which has coordinates minus square root of E0 and minus square root of E0. S4. And finally, we have signal S5 with coordinate square root of E0 and minus square root of E0. It goes in the last portent. S4. Okay, and this is how our signal space looks like. So we have signal in the middle, in origin, and we also have 4 points in different orbitals. And now actually I slightly confused the tasks, but it's fine. It's fine because we need to draw first signal space. Okay, this result corresponds to part F actually, because at part F they asked us to draw signal space diagram, but we also have to complete. Now let's go back to part E and let's plot time domain signals for all these 4 remaining signals vectors. So let me move signal space down. We come to this part in a second. Before we come to signal space, I will show how time domain signals will look like. S2 of t. So S2 of t was red color. Is 0, it's nothing. Then S3 of t. Yeah, we need to think about S3 of t. In order to answer this question, I need to copy both basis functions that I have. I will copy the first basis function. I will place it nearby. And also I will copy the second basis function that I will place below. And now we try to analyze how the time domain signal will look like. Okay, for first signal we have minus of first basis function plus second basis function. I can show that we have minus first basis function overlap it with plus of second basis function. And if you look to this second basis function, you see that if after we calculate this difference between second basis function and first basis function, you will get pulse in the second part that goes from t over 2 to t over 2. And amplitude will be 2 times u0. Then if we go next, and plot signal S4, we have minus first basis function minus second basis function. Oh, but actually I could keep. So we have this yellow dashed line corresponds to minus first basis function. And then we have, if I flip second basis function, I also have minus sign. And if we combine both of them, we get that we have a negative pulse in the range from 0 to capital T. Oh, sorry, to capital T over 2. From 0 to capital T over 2. And in the range from T over 2 to capital T, we have nothing. Simply speaking, we have nothing. So, and the last signal, the last one, S5 of T, we have plus positive part of first basis function and minus second basis function. If we combine them, we get negative pulse that goes from minus T over 2 to capital T over 2, and amplitude should specify amplitude. It was minus. It was 2u0, then it was minus 2u0, and for the last signal we have again minus 2u0. T over 2, capital T, 0, and small t. Now we have time domain signal for all 5 signals. And what's interesting here, we have interesting part is the following, that actually we have almost the same signals as we had in the previous task. But look how our basis functions look like. You see that we have such 2 basis functions where one comprises 2 pulses with different sign, and for second base function we have this one long rectangular pulse. But if you look to our basis function on the previous task, you see that we have these 2 rectangular pulses at different positions. Yeah, this is our. And I copy this. It was our previous second basis function. And okay, they have slightly different scaling, but at least you can conceptually they can explain you what happens there. Conceptually they correct, but have slightly different scaling. Okay, you see that you have different pulses at different positions. This was first set of basis functions. Now we have another set of basis functions that explain exactly the same signals, but they look like differently. And this is idea for that basis function or basis set of basis vectors is not unique. You can have different versions of this basis vectors to represent exactly the same set of signals. And there is nothing wrong. This is just what we have. Okay, let's go back. Now we come back to our discussion about the signal space itself and about the signal space diagram. Now we need to assume that signals S1 to S5 are used for this formulation with 5 positions, and we need to indicate the decision areas according to the maximum likelihood decoding in AWGN. And we assume that all signals have the same probability. And here, this part is tricky. You should be quite careful when you see such task on exam. But if you follow our original procedures, then you don't have any problems. So you have 5 points. I can show again. You have point for S1. You have point for S2 in the middle. You have point for S3. You have point. Oh, I have 2 points for S4, and it is wrong. I think this red one should be S5. S5 and S4. Okay, and now I need to choose nearest neighbors and plot decision boundary between nearest points. So what are the nearest points? Nearest points are S1 and S2, S2 and S3, S3 and S4, S4 and S5, but also we have to consider points S1 and S3. They're not nearest, but we also have to consider them. So, and what we do, we start with nearest points and we plot boundary. We find middle point between them and, but they're not aligned with axis. Oh, sorry, not axis, but with grid. I need to shift a little bit. Okay, now it's better. The middle will be here. And I plot orthogonal line. Orthogonal line, like this. For all nearest neighbors. I don't go beyond intersection because then after I considered all nearest neighbors, I go for other neighbors. And if I look to S1 and S3, my point I might receive something, for example, at this region. And I also need to specify what will be the boundary between points S3 and S1. And I also choose middle point, and I also plot orthogonal line. I don't go closer to S2 because this region corresponds to symbol S2, and I need to go above because I need to specify what happens between S3 and S1. And I continue this for all directions. I mean, for the rest of not the nearest neighbors, for example, S1 and S5. And this is how this boundary will look like. And again, I don't go closer to S2 because this is a region. If you, for example, if you continue and put, or no, if you consider a point, for example, this point, and you want to plot boundary, then you just need to analyze what's the distance to different points. And you see clearly that distance between S1 to this point, S5 to this point, and S2 and this point clearly answer you to the question, which point you should, which decision area you should choose, because this point is closer to S2 comparing to S1 and S5. And for this reason, we make this boundaries just going to infinity, but not closer to S2. So these are our boundaries. And now I can show with different colors decision areas. So in the middle, we have area for S2. And then we have, okay, let me show with the same color two different areas, but of course they correspond to different symbols because I have a limited set of colors. So this is how decision areas look like. But in general, they should have different colors. Okay, are there any questions? Okay, once again, let's try to discuss how we plot these decision boundaries. Decision boundary explains, it just explains where we have border between different decision areas. So if a point, if we receive something in special region, we make decision corresponding to the point, to the constellation point that belongs to this region. So if we have anything received in this region close to S1, then we say that this point corresponds to something else S1 plus noise that we have in addition to our point S1. So, and we do the following. First, what you do, you consider nearest neighbors. So we have nearest neighbors S1 and S5 or S2. Yeah, in this special case, S2 will be nearest neighbor to all other points. And then you just choose middle in between these 2 points, S2 and S1, and you plot, or maybe you plot lines that go through the middle between 2 points. But of course, this line will be going like this. It will go to infinity, yeah? But then we need to analyze what actually happens that if you have point that is you simply speaking, you need to simplify these lines and remove some parts, trying to analyze to which region belong each part in this region. Because if you consider, for example, point in this region, and you just try to think where you should put this point, to which signal this point will be closer in our constellation. You just can measure distance to different points, and then just put this whole region, you just put to this part that closer to our point. And here we see that this point will be closer to S1. As a result, regardless that we have this line going to infinity, we just remove it. We remove it, oops. And we just put the whole region belonging to point S1. And the same you can do for all regions that might be unknown for you at the beginning, because there you have many different intersections. Yeah, you start with intersection. So, sorry, you start with boundary between nearest neighbors, S1 and S2, and then you get these lines in the middle. And also you should plot lines between other neighbors, for example, as S1 and S5. What else? And I think in general that's all, because also you can say that let's consider points S1 and S4. And if you consider S1 and S4, then I will show, then probably you should put boundary like this between S1 and S4. Yeah, between this will be optimal boundary between S1 and S4. But if you look that this, where this boundary is located, this boundary will go directly through point S2, S5, and S3. And you have to take into account these other symbols as well. And as a result, if we start discussion, if we start plotting boundaries starting from the nearest neighbors, then we go to second set of vectors that close enough, and we consider points with the largest distance in the very end. And typically we don't come actually to discussion about points that have the largest distance, because all space will be already divided for special regions, as we have here. So we started with points S2 and all other points. Then we discussed points S1 and like points S1, S5, S1, S3, S3, S4. And then after we get already the whole region separated for, the whole space separated for specific regions. Okay, this is the idea, but yeah, you guys. You start with nearest neighbors and then gradually increase distance between, or start to consider points with larger distance between points. Okay, other questions? Is it better now? And the last question that we have here, we need to determine mean energy per symbol as function of E0. So here we have that energy of first signal, the same as energy of third signal, fourth signal, and fifth signal. And it equals to E naught. For the second signal, as far as it equals to 0, energy also equals to 0. And average energy we just need to calculate sum and divide by number of symbols. And here you clearly see that average energy will be 4 over 5 E0. And the last step, that if we calculate, okay, we cannot calculate logarithm of 5, but actually that's all, because the last question could be what is the mean energy per bit, but we don't have even number of symbols for this task. So this is end. This is the last part that we have. This is average energy, mean energy per symbol in terms of E naught. Okay, are there any questions for the materials we discussed today about signal space and how we find it, about Gramsci optimization procedure, about anything? Okay, if not, then I would like to thank you for your attention. And tomorrow we have another tutorial where we revise other tasks from previous exams, and you are welcome to join us via Moodle. You are welcome to join via WebEx tomorrow. And let's see, I will say either, I think I send you tomorrow morning the link, but we don't have on-site tutorial. It will be also via WebEx. Okay. But tomorrow, I think we have seminar, lecture. Lecture you have at 11, and instead of lecture, we have seminar. Okay? Okay. So, thank you. I wish you a productive day and see you tomorrow. Goodbye.